Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on the family of error functions. And in the previous lecture, we looked at all the functions that are related to the error function, such as inverse error function, the imaginary error function, scaled complementary error function, Fediva function or W of z, Dawson function, also the derivative and integral of error functions. So error function in general is a very nice function. It's very easy to implement. And now I want to look at the other error function libraries that are out there for Java. As you have probably guessed, there are two libraries. One is the Apache Commons Math, org.apache.commons.math3.special package. So this is the Apache Commons Math, and in the org.apache.commons.math3 we have a package called special. And in the past we looked at the Bessel J and beta and gamma functions. Now we can look at also the error function itself. And the other one is Michael Flanagan's library, flanagan.analysis. In the analysis package there is a class called stat, and it calculates or evaluates the gamma function based on the statistical gamma distribution, right? So it has a static method called ERF, error function. Now, what are the problems? So the problems are, these are static calls and the implementation is not going to be as good as the way I implemented them. But more importantly, these implementations don't have any support for complex numbers whatsoever. And this is traditionally a problem with scientific computing in Java. For some reason, complex numbers were never basically standardized and were never extensively used in Java libraries. So I want to create a Java test class and test three libraries. One is my implementation, the other one is the Flanagan, and the other one is Apache Commons Math, and compare the speeds. So I have already done one such test, and my library evaluated 1000 error functions in 44 milliseconds. Flanagan completed in 78 milliseconds, and Apache Commons Math completed in 79. So we have a better implementation than the other two. So let's head to Eclipse. Here what I want to do, I want to create in the tests package, I want to create a new test class called test error function speed, and I want to have a main method. Alright, so we're going to have three tests, test 1, test 2, and test 3. Alright, so let's comment out test 2 and test 3, and test 1 is going to be from my library, the special, and we want to see how long it takes. So as you're already familiar with the implementation, we just create a public, a static, void test 1, right? Here we create our error function first, error function func new error function, and then we create our values. X is, I'm going to evaluate for real numbers, so math utils, len space from -5 to 5, let's say 1000 points. All right, and then double error func, which is, we call our array func apply. This is just a for loop underneath of this apply method. And then we call the func.error func of basically a double value t, and then we apply it to the x array. All right, this is just evaluation. As you see, using the lambda expression is very elegant of calculating a function of an array. There are other ways which actually I will look at in this lecture also. But for now, this lambda expression and this apply method just encapsulates a for loop, so we don't need to write the for loop each time. And obviously next I want to plot it, MATLAB chart, fig new MATLAB chart, and then fig.plot x and error function with color B, fig.render plot, fig.show with the exit flag to terminate the JVM once we close. All right, So let's run this, and as you can see, it works fine and we get the result. And as I mentioned before, the main change in the error function is typically in the -3 to 3 interval. Outside of that, we can really assume that the error function doesn't really change that much. All right, now I want to time it. So timer, new timer, and I use the timer from my library, mathlib.util. You can also use the one in stern.cold, but I'm using mathlib.util. And timer.start, this records the system.millisecond time from the system library. And then timer.stop, it gets the time again from the system library. And timer.show, it just prints it to the console. All right, so this is our first test, which is my implementation. It takes about 60 milliseconds. If you run it again, we have to run multiple times, and it takes an average. So 51 millisecond, another one 56. So let's say about 50 millisecond, right? Or 55. Let's say 50 millisecond on average, or 55. So test 2 is going to be from Flanagan library. All right. So in test 2, let's just copy and paste the whole thing. And in test 2, what we are going to do is, let's remove this because we're going to make a static call. And here, if we go to my mathlib reference libraries, and these are all the scientific computing libraries out there for Java. So we have this Flanagan, and in the analysis package, there is a class called stat, and if I decompile it, we can look into this stat class. And here there is a method called error function. Let's see. Here, so it's on line 10,115. Takes the double value and returns the value of the error function. So we're going to make a static call to this stat from Flanagan.analysis error function of t. All right, so test 2 is here. Let's run this. It takes 97 milliseconds, and we get basically the same result, right, as before. So let's run it one more time. 95 milliseconds. Let's run it one more time. 91 milliseconds. So let's say this takes 91 milliseconds. All right. Now the last test is basically from the Apache Commons math. So we're going to again make a static call to an error function in that library. So from Apache Commons math. And again, we're going to copy and paste test 2, rename it to test 3. And here, so if you go back and look at the commons math, and here in the org.apache.commons.math3, there's a package called special, and here there's an error function, and it's a very small library. And we have this error function double, error function complementary, error function of double, and error function inverse. So it uses a polynomial approximation for the inverse error function, and error function complementary inverse, which is error function inverse of 1 minus x, right? All right, so let's go back here. So we are going to use the error function from org.apache commons, and then call the error function for t. All right, so this is test 3, and we see about 85 milliseconds. So let's run it one more time. 90 milliseconds. Let's run it one more time. 86 milliseconds. So we can conclude that we have 86 milliseconds, right? So as you can see, our implementation is faster, almost a factor of 2. And We had also very good accuracy, so if you find so whatever you find out there may not be always the best implementation, so you can always try to do your implementation also, and then do a benchmark. This is a simple benchmark. It's not very accurate, but it gives us a feeling of how good these different implementations are. All right, so back to our PowerPoint. Now, there is another interesting thing, as I mentioned, is the fact that so we have now these functions, these special functions, or regular functions like sine and cosine. And then we are trying to evaluate them for large arrays, right? An array of large numbers. So how do we handle these large arrays, right? So assume we want to evaluate an array of some numbers. Let's say the array has 1,000 elements, or 1 million elements, or 100 million elements, right? Now, so far, in all of my tutorials, even here, we just use this apply. And this apply is nothing but a for loop, right? It takes an interface, a functional interface, which I always use it as a lambda expression to have a more elegant code. And then it's just basically a for loop. And for loop means, you probably are familiar with this term, sequential calculation, right? Sequential evaluation, which means we go through each element one by one, right? We don't go and take different elements at the same time and process them at the same time. So this is sequential evaluation, right? And this works fine when we have a small number of elements, let's say 1,000. It's still pretty small, but once you go to 1 million or 100 million, sequential evaluation really costs a lot, because especially if your computer has many cores, so you can definitely take advantage of all of that computation power simultaneously, right? So in order to compensate for the problems of sequential evaluation, we can go to parallel calculation, right? So again, sequential calculation means we iterate and calculate one by one. And that means that in Java, we always launch one thread, right? Let me just write it here, one thread. So this means, let's write it here with another color, one thread. So this means only one thread, right? And then Java supports multi-threading, so we might be able to take advantage of it in cases where sequential calculation is not very effective. Let's say if I have 1 million elements in the array and I want to calculate or evaluate the error function for that 1 million elements, right? So in parallel calculation, we divide in pieces or split the array in pieces and calculate in parallel. This is obviously multi-thread, right? And if we use advanced data types such as array list or list, we have something called a splitter, I believe, and that means it splits and creates iterator for all the splits, right? So this is one concept. And again, a simple for loop is good for a small size arrays, because for loop is basically a sequential calculation, and if the size, actually this should be like 10,000, not 1 million. If the size is less than 10,000, we typically want to stick to sequential calculation. Not only we don't gain anything if we go to parallel calculation for this kind of size, but we also lose something, because launching parallel calculation, it has some initial cost of launching, because you have to split, right? It has two phases: split, calculation in parallel, and then merge. And a split and merge may cost more than what the parallel calculation pays off, right? So for small size arrays, a split and merge definitely costs more than doing a sequential calculation, right? For larger sizes arrays, we have the wonderful Stream API in Java 8, and we can fully take advantage of them. Actually, we can use a Stream API for both sequential calculation and parallel calculation, right? And these are very easy to use, especially with arrays and lists. So they completely work behind the scenes, so the user doesn't really care about the implementation. If you want to use sequential calculation of an array, call the arrays class .stream and pass in your array x, right? This takes the array x and returns a sequence, basically returns a stream of data types that are inside the X array, a sequential stream, right? But if you call arrays.stream X and then call the parallel, it returns a parallel stream, right? So if we go to 1 million or 100 million elements, we want to use the parallel stream instead of the sequential stream, right? Now, significant difference, we may notice significant difference when we're handling double arrays of size, let's say 1 million or more, right? And the example here is calculate the error function for, let's just say 1 million. We don't want to go a very large number. So significant difference when handling arrays of size 1 million or larger. So for double numbers, let's say we want to calculate the error function for 1 million times. So here's the function that I wrote using the stream API. So I create my error function, I create my array double X from -5 to 5, 1 million elements, and I set my timer on. And then I use, so this one is the original for loop. The second one is using the sequential calculation from stream API, which is very similar to for loop, but it has a little bit of overhead for launching the stream and then collecting to an array. So we expect that if the size of the array is very small, or even for the large, so the for loop should be slightly faster than the sequential stream. But then we can also launch our stream and convert it to parallel and then do the evaluation, which I use the map function, and then collecting it to an array. All right. So one benchmark that I did for the simple for loop for 1 million elements, I got 990 milliseconds to evaluate. But with the parallel stream, I got 560. So almost a factor of 2, right? So how do we use this stream API with arrays? So we use the arrays class and .stream, right? So we get or create a sequential stream out of the array. And then we use the map function, which takes a functional interface, a lambda expression, and we put our function as a lambda expression or a method reference. We can also use a method reference here. And then these are called intermediate operations. These are not terminal. And then if we want to collect the result into something, let's say I want to collect the result of the mapping into an array, a double array, I use a terminal operation called toArray. And this closes the stream. And if you are familiar with the streams, you already know that the streams are kind of a lazy operation. So unless you call a terminal operation, none of these mapping and stuff get evaluated. So when we call the terminal operation, all the previous stream operations, all the mapping and stuff, or the manipulations start to evaluate, right? Now the situation is even better or more interesting when we try to evaluate the error function for complex numbers, right? So what I do here, I create my X and I want 1 million terms. I want to evaluate the error function for X plus J. Imaginary numbers or complex numbers with a fixed imaginary, which is J. So I create a list of complex numbers, right? And it's an array list, and initial size is x.length, and then I write a for loop to populate my list with X plus J, right? Set my timer on, and then so now the problem with the list here is that when we call the parallel stream and call the map, it works fine. But once we collect it to an array, it returns an array of object, not an array of complex numbers. So we have to do a downcasting at some point if we want to actually downcast or cast them to complex numbers and use them as complex numbers. But this just returns objects, an array of object. All right. Now we can collect it to another list, so we can call the collectors and collect them to a list, and I believe in that case it's going to collect to a list of complex numbers, right? Now here you really see the difference. So with the for loop or a sequential stream, I get 33 seconds to evaluate 1000 complex terms. With the parallel stream, I got 6.8 seconds. So it's like a factor of 4 or 5 improvement. All right. So the lesson here is that don't use parallel stream for small arrays. If your array size is less than roughly 10,000, then just use a for loop or a sequential stream. If your array is very large, more than 10,000, let's say you're approaching 1 million elements, then definitely use a parallel stream. And these are extremely easy to use with arrays because you just call arrays.stream, or if it's a list or a collection, they already have the stream built in. So it's very easy to access them. So I just want to go back to YouTube and give you a demo. So back to our test one here. So this apply again uses just a simple for loop. So let's run it one more time, 51 millisecond. And now I want to use a sequential stream. So what I need to do, I create my double error function values. Here I call the arrays class, which is a built-in class in Java, and then call the stream of double array, int array, long array, some type t. And so we're going to call the double array and pass in my x. All right. So what this returns is stream of it's a double stream. Again, it's a built-in stream of type double that handles double types. And then I want to call the map to do some manipulation, and double unary operator. This is a functional interface, so I can call func dot dot or colon error function. It's a method reference. And then what this returns, again, a double stream, right? Because this is an intermediate operation. So it takes the stream, does some mapping, and returns again returns a stream. So now I want to collect it to array, right? And this returns a double array. So you see, this is extremely easy to take a function and then apply it to all these values, right? So 56 millisecond, so not that far from 51 millisecond that we saw, 55. So about 4 or 5 milliseconds overhead when compared to just a for loop. And that's because just opening and closing the stream takes some time, okay? Now let's try to do a fancy thing and go and try to evaluate this 1000 elements for parallel stream. Again, the code is very similar. Arrays.stream of x, this returns a double stream, and then we want to call the parallel, which returns a parallel version of the double stream, and then we want to do a mapping. T goes to func.error function of double t. Again, this is an intermediate operation, so it returns a double stream again in the parallel sense, and then we want to terminate it by collecting to an array. Now, what we expect here is that this parallel stream should add overhead cost of computation to do the splitting and then merging. So, and because the size of the array is small, we should actually see a worse number than 56 milliseconds. 56 milliseconds. So in this case, it's not that worse. But let me run this one more time. 59 milliseconds. But it's very interesting. The result is completely nonsense, right? It's completely wrong. Why are we getting a wrong answer when we go to parallel? So as you can see, if I go to sequential stream, 56 millisecond, and the result is correct. This is the error function. But if I go to parallel stream, as you can see, 59 milliseconds, so a little bit worse. But more importantly, the result is wrong. It's absolutely wrong. So why is the result wrong? That's because we are using parallel streams, which means we are in the multi-thread domain, right? We're using multiple threads at the same time, and unfortunately our error function implementation is not thread safe. So why is it not thread safe? Because of the functions. These functions, error function, large argument and small argument, they depend on the state of the object, right? Because we have these field variables, these instance variables, and if two threads try to invoke this method at the same time with different x, remember threads have different values of x because they split the original array into multiple subarrays, right? So if two threads try to get to this method simultaneously, then they end up with different x values, so different lead terms. So if one thread gets to this method a little bit before another thread, and let's say by the time it gets to this evaluation, the other thread has already changed the value of lead term, so eventually this sequence or this sequence gets evaluated in a wrong way because the fact that this sequence depends on this value, which is x squared, right? So what can we do? There are two ways. So here we are dealing with the problem of thread safety and something called race condition, right? So multiple threads, they don't add much here, but even if they did add much in terms of computation cost, they were faster when we go parallel. We still have the problem of this race condition because our implementation wasn't thread safe. So there are two ways or a couple of ways to basically remedy the situation, fix it. And obviously one is to make it thread safe, and the first approach is to put a manual lock. So we go synchronized. Let's see, well, how do you write it? Synchronized. All right, so we go synchronized, and this forces the threads to wait until another thread that is using the method is done with it, right? So if I run this, I hope I get the right answer. Yes, so now we don't have a problem with thread safety and race condition. But then the problem here is that we are basically defeating the purpose of having multi-thread implementation, because this puts a manual lock on the method, and if two threads have different x values and they want to go in parallel and evaluate in parallel, they cannot, because this method says, okay, I'm synchronized, all threads must wait until the current thread that is using this method is finished, and that defeats the whole purpose. It's like we're doing sequential, right? And in order to see the severity, I want to increase the numbers to 1 million numbers. And let's remove the synchronized first. So if I go and use my sequential evaluation for 1 million elements, I get 810 milliseconds, all right? Which is not bad. Now, if I go to parallel, hopefully I'll get a smaller number, which means the evaluation takes less time. Obviously, it takes less time. So from 890 or 900, we went to 338 milliseconds. So it's almost a factor of 3 improvement, right? But then the problem is that the evaluation is wrong. That's because our method is not thread safe, our function. So if I put the synchronized here, synchronized, then as you can see, the parallel stream doesn't help any much. Actually, it gets worse. It gets worse, even worse than sequential evaluation, because it puts a lock, putting the lock and all threads waiting and then jumping back and forth between different threads in that method. It costs a lot, right? So synchronization it's not an option if we want to gain overhead, right? This sequential was 800, about 900. We're going about 2000, so it's a factor of 2 worse. So absolutely not worth it. So the other thing that we can do, instead of locking the method itself, we try to fix the problem of the method depending on the state, right? So if I try to set this to double and double, so I change all the global variables, all the field instance variables to local, so sequence, right? But then there's still a problem of the fact that so we are creating too many objects, local objects, and eventually if we call the method 1000 times, then the garbage collector has a lot of abandoned local objects to collect, and that causes a little bit of overhead, which is very well worth it for parallel stream, but definitely not for sequential stream. So let's convert these two, double. So now our implementation for both the small argument and large argument of the error function, they are independent of the state of the object. They fully rely on the local variables. So now if I run the parallel stream, it must work fine. It should be correct, because even if there is a race condition, then the different threads don't interact with each other, don't affect each other. And as you can see, it is correct, the evaluation is correct, and the evaluation time is also very good, a factor of 3 better than the sequential stream. So if I launch the sequential stream for 1 million terms, this should evaluate to about 900 something, 1000. As you can see, now we're getting so in the previous case it was 890, 900 milliseconds. Now it's 1090 milliseconds, so about 100 millisecond worse. And the reason is because of the local objects that we're creating, all these local variables that are subject to garbage collection, right? So if I go back to let's say the instance variables, right? And this was the whole point of trying to squeeze more efficiency by not creating many objects, many local objects. And then if I run this again, it should be a number smaller than 1000, because now we're not creating as many objects as before. 830. So we are about 100, about even 200 milliseconds better than before. But again, in this case, we still have the race condition. So it's a trade-off. We can lose a little bit in the sequential, but then our implementation is completely fine for parallel, which is actually the best way to go. But for now, I'm just going to keep this as instance variables, i.e. the method depends on the state of the object. And because in most cases, in most examples I'm going to show you, the number of evaluations is not, it's always around 1000, 2000. So in those cases, parallel stream doesn't make sense, and we use sequential stream, and this implementation works fine because sequential stream is only one thread, so there is no need for thread safety or any problem with the race condition, etc. All right. So to recap, we can, instead of trying to write something like this, apply, and which underneath of it is just a for loop, we can always use the wonderful Stream API. And a Stream API comes fully equipped with sequential or parallel evaluation. When the size of the array is large, typically larger than 10,000 elements, we tend to try to go parallel. But in parallel, we have to be careful about the implementations, especially the thread safety and the race condition. And that is very important when our method depends on the state of the object. And if any of these parameters change the instance variables that are related to the state of the object. In this case, you see both this lead term and val, they change. And the reason I implement it like this, because in sequential evaluation, we're not creating as many object references. So garbage collector has an easier task to do because less object references. All right. And then we clearly see that effect in the fact that when using the instance variables, we're gaining some computation efficiency. So if I go back here and change these to double, change these back to local variables, right? And then double here, double here. So the evaluation of the error function is now fully based on local variables. So even if two threads access these methods, it doesn't matter. Each one gets its own local variables. But here in the sequential stream, we will lose a little bit of efficiency. So we go to 1000 instead of 800. So it's like 200 millisecond, which might not be very good. But when we go parallel, now we're gaining quite a lot. So we reduce this number by a factor of 3. Okay, in this case, it's not that much improvement, but at least a factor of 2, we see that. 315. So, and the reason is even if garbage collector has more stuff to do, but because we are computing in parallel and the split and merge are not the main contributors to the cost of evaluation, because we have 1 million evaluations. So definitely the cost of evaluation here is the dominant. So I hope you enjoyed this lecture, and just remember that Stream API is a wonderful